Hey, Vlad here, devinside.com. Welcome to another video. This is part 2 of the Tagless final series, and contrary to the previous video, today we're gonna get more handsy with the code. Let's get right to it. Alright, so what we're going to do today is two things. Firstly, we're going to take a look at the canonical tagless final example. This is the same example that is used in the tagless final paper, which you can find in the description below. We will follow the paper just a little bit, but we will diverge from it relatively fastly because it gets very specific and we don't need all of these details. Another thing that we will do is we will start taking a look at the to-do app that we wrote a couple of years ago in the cake pattern series. We're not going to touch it though yet. Now, you might be wondering why we're bringing a to-do app into this, and I'm glad you asked. See, when I was learning Tagless Final, the hardest thing for me was to visualize where I would put all of these things in a real-world application, which in my opinion is one of the cornerstones of maintainable software. Where do you put stuff? So what we're going to do is we're going to be constantly jumping around between the example from the paper, which is the solution to the expression problem, and the to-do app, so that I can start saying things like, okay, so we now learned about the DSLs, and the DSL would live over here, and now we learned about the interpreters, and the interpreters would live over here. In fact, why don't we start with the to-do app right now? As in most of my videos, I'm using an Ubuntu 18.04 virtual machine, and I'm using Windows as a host. Windows has a virtual desktop feature, which gives me shortcuts that allow me to switch between the desktops like this. I'm in Windows and I'm back into Ubuntu, which pretty much looks the same because they're using the same wallpaper. So if I were to go to Windows, I already have it open in my Chrome over here. So everything is going to be on GitHub, and during the entire series, we're actually going to be having commits pretty much at the end of every video. At the end of this video, we're going to have a commit. All right, so this is a repository. The link is going to be down in the description, but please make sure, because I'm buffering my videos at the time you're watching this, this repository might look different. It might be, already complete. So make sure to click on commits and then select the commit from the video. And, starting from this video, actually in the description, there will be a link not just to this repository, but also exactly to the commit from this video. As you can see, there are two folders, and both of these folders, and I'm using an extension called Octatree. Each folder is an individual SBT project, right? So there is no relation between them. I just wanted to have both of them in this one repository. So I already cloned this repository in Ubuntu over here, and I'm using workspaces. And so in the top one, I have the expression problem open, and at the bottom one over here, I have the to-do open. So what we're going to do now is I'm going to relatively quickly run you through the to-do app, so that later when we learn about the DSLs and I'm going to say, okay, it's going to live over here, I need you to understand what over here means. All right. Okay, so the first thing is that this is a multi-build, and it's cut into these 5 sub-projects. There's a domain, core, delivery, persistence, and main. Notice that the folders have numbers, and I'm starting to use this more often actually in multi-builds these days, not only when I record videos, but actually in my projects as well, because these numbers, they essentially denote the dependency graph. So without looking at the build, you know that everything at the layer 2, for example, which is core, has a dependency on everything on the layer 1. Everything on the level 3, which is both of these things, they have a dependency on core and therefore on domain. And then at the very bottom, you have the main. All right. We can relatively quickly look at the build, and we're going to see that we have the to-do, which is the multi-build, the aggregated build, and we have the domain. It's at the very top. Notice that the project doesn't contain the 0, 1. Okay, so we have the domain, we have the core. The core depends on the domain. All right, then we have the delivery depends on core. We have the persistence depends on core. We have main, it depends on delivery and persistence, and therefore it depends on everything else. It's a very simple build. There are no dependencies. We see a couple of dependencies here. They are for tests. It's just that because I use the same template as I use when I create all of my projects, and these guys were already there, so I didn't remove them. We actually don't have any tests, and I'm not sure. Maybe at the end of the series we will start adding some tests. But for now, we have the domain, core, delivery, persistence, and main. All right, so the first thing that I'm going to do is I'm actually going to start SBT real quick. I'm going to go over here, terminal, and I'm going to start SBT. While it loads, I'm going to go into the main method. All the main method is doing is that it creates a dependency graph. It passes some stuff in, like in this case, the datetime pattern and whatever, but essentially it creates a dependency graph .dsl. Now, this to-do app is not written in Tagless final style yet. However, in the preparation for the series, I took the to-do app that we wrote 2 years ago. I rewrote it into the Tagless final style. While I was doing it, I improved it a little bit. and then I converted it back. And therefore, I prepared a couple of things so that we don't waste too much time. Okay, so it's called DSL over here, but actually all it does is that it returns an instance of this controller. Okay, as of right now, I'm going to go to main, so I can do cd main. Notice that we have like all of these aliases, and I can just do R for run. And if I go make this a little bit bigger, in fact, maybe I can go in full screen like this. All right, so as you can see, this is an interactive application, and every time we just type enter, and we don't hit any of these commands, it's just gonna show the main menu, which is this one. Okay, so every time I press enter, we see the main menu. All right, and I'm also generating a random color for this line, just so that if I hold enter, you see that something is actually changing, that this thing is actually working. Okay, so for example, if you wanted to create a new to do, we would type in C, we would type in the description, for example, something like buy milk, and we would enter a deadline in the following pattern. So for example, 2020, let's say it's the month is going to be 5, it's going to be May, and it's going to be 3. I believe today is actually 3rd of May. And right now we have 12:09. All right, so now we created this to-do. It says successfully created new to-do, and we can type in something like show all to see all of the to-dos, so SA, and we see all of the to-dos, right? So it's a very simple to-do application. And by the way, there are no dependencies, so we're not using any databases, we're not using any web frameworks, anything. Okay, there are 0 dependencies right now. All right, so we can do a couple of other things, but you guys can clone it and you can play around with it for yourself. There's also like a teeny bit of error handling. So for example, if I created to do, I type something in, but then I mess up the format, it's going to say that this thing doesn't match the required format. So if we show all again, we're going to see that we still have only buy milk. And, we can update the description, we can update the deadline, blah, blah, blah. Let's for now just exit the application and actually look at the code just a little bit. All right. So I'm actually going to close this. Okay, so we have the controller, and notice that we have the breadcrumbs. So if I have the tree view collapsed, you should still be able to see exactly where we are. Okay, so if I jump in there, I'm using metals, then you will see that all it is doing, and as you can see, I already prepared it for Tagless Final. I'm not sure if you can see this. If you have never seen Tagless Final, maybe you can't actually recognize it, but it is already prepared. Like for example, like these parameters, they're implicit, but they don't need to be implicit. I just wanted, I didn't want to change that much code. Okay, I just wanted to show you that you can do like things like effect tracking, without Tagless Final. Okay. So this is a simple constructor dependency injection. We're creating a controller. The controller needs a pattern, which we pass from the main, and it needs a boundary. And we're creating a boundary, and the boundary needs a gateway for the data, right? So this is basically it's mimicking the database access, and it's using the in-memory entity gateway. Right now we're going to learn about DSLs and interpreters and programs, like these 3 things. Remember I told you, to remember the titles from the book. Structure, interpretation, and programs. Structure is the DSL, interpretation is the interpreters or the evaluators, and the programs are basically programs. So for now, this is going to be the program. This is going to be the controller that is going to decide which part of the DSL to call, right? And the DSL is going to be the boundary. It's going to be the boundary to the application, right? So the controller decides, basically whether it's going to be a web application or whether it's going to be a terminal application in our case, okay? This is going to be the program. This is going to be the DSL. We can actually jump in there. So boundary is a trait. Let me collapse this, boundary and an object, okay? So this is going to be the DSL. Okay, just a trait with a couple of methods. Okay, and we're going to have the implementation of this trait. Remember, in the Tagless Final, the implementation of this trait is essentially the interpreter. Okay, so inside of here, I'm not sure if I will be able to collapse it. Okay, but basically we have a function called DSL. It takes the gateway and it produces the boundary. Okay, so technically this is the interpreter, right? Everything over here is the interpreter, but because the return type is the DSL, I call this method DSL. Okay, so this is just the implementation of this trait. Okay, so now we have these 3 things. Okay, so we have the controller, which is over here, which pretty much looks the same. Controller is going to be our program. Let it stay. We're going to have the boundary. The trait of the boundary is going to be the DSL, and the implementation of the trait is going to be the interpreter. These 3 parts. For now, this is all we need about the to-do application, and we can go up where I have the expression problem open. The expression problem only has the main. If we go into SBT, and we will run it. So I go into SBT, and as you can see, like all of these guys are empty, right? So there's a .keep file so that GitHub is happy. Git and GitHub are happy, but all of these are empty. Okay, so if I collapse everything, you're going to see we're going to have DSLs, interpreters, and programs. So this was the controller. This was the controller. This was the trait boundary, and this was the implementation of the trait boundary. And by the way, let me jump to the to the to-do app again. So we actually have more DSLs than this. Okay, if I go actually to the folder over here, we're going to see we have the boundary and we have the entity gateway, and it looks exactly the same. Entity gateway is a trait, right, which means it's a DSL, and somewhere where we are deciding that we're going to store stuff in memory, which is over here, we're going to implement this interface basically, right? So this is going to be the interpreter for the database layer. All right, let's go back up. As I already said, everything is empty. Okay, we can go over here and cd into main and just basically always, always run our applications like this. As you can see, it's just a main. There's nothing special in there. All right, so this is all we needed to know about, about the structure of the two projects, and now we can actually start walking through the expression problem. So what is the expression problem? Well, the goal of the expression problem is to answer the following question: how can we add code to our application without recompiling the existing code? And Tagless Final will allow us to add DSLs, interpreters, and programs without having to recompile the existing code, which sounds like a miracle, but it actually is possible. In fact, a couple of years ago, I made a video about dependency inversion, in which I claimed that dependency inversion is pretty much the only trick that we have. I called programmers as one-trick ponies. This is the only tool that we have for maintaining, applications and making them scalable. We even have a joke about this. Every problem can be solved with just another layer of indirection. And so the reason we're using a multi-build is so that I can clearly show you which parts are being recompiled and which parts are not. Now, it's called the expression problem because the original example for this problem was in the domain of simple mathematical expression problem. Now, before we start writing any code, let me actually show you how we can find the original paper. Sure, the link is going to be down in the description, but still, if you go to the website, which I already have it open over here, it's called okmij.org. I'm not 100% sure, but I'm pretty sure that OK stands for Oleg Kisilov, who is the Russian professor who wrote a bunch of these papers. Okay, it says you're probably looking for this, and if you click on this, you end up on this page. And if you go over here, there's a bunch of information here, a bunch of papers. If you click on Tagless Final over here, then there is a small description, couple of papers. It says that this was the initial paper. However, the very initial paper, and Oleg Kisilov actually says it himself. I've seen presentations for him. He refers to this one. This is the one that I mentioned in the previous video called Extensible Denotational Language Specifications by Robert Cartwright and Matthias Felleisen. All right, but essentially the paper that we're talking about today is going to be this one, the very first one, Type Tagless Final Interpreters. The first introductory course was published lecture notes. So if you click over there, tiny description, and there is a PDF over here, lecture.pdf. Okay, so I'm going to have both of the links in the description. We're going to have this one and to the actual paper. All right, so let's finally start writing some code. So we're going to go over here and let me open the tree view, and we're going to collapse everything. Let me leave the main over here. All right, so we're going to open the DSLs, and as I already mentioned, it's empty. So we're going to remove the keep file. We don't need it anymore. Yes, delete please. Okay, and we're going to create a new file, source main Scala, and we're going to call it expression problem, right? So this is basically the package. Then we're going to have the initial encoding or initial embedding, and we're going to create exp.scala, right? So this is going to be the mathematical expressions. All right, so I prefer to have my packages structured like that. In fact, I'm realizing right now that I forgot to create the dev inside you folder. So it's going to be source main Scala, and over here there's going to be a new folder dev inside you like this. I'm gonna move it in there. All right, okay, cool. So yeah, like this, package and package like this. Let me collapse the tree view. All right, so as mentioned in the previous video, the initial embedding, the initial encoding of the problem is by using an ADT. So in Scala we do a sealed abstract class exp extends product with serializable, which is a bit of a folklore in Scala. And now we're going to have a couple of forms of this ADT. So we're going to have final case class. So we'll be able to use literals, and it's going to be an integer. And by the way, by the end of this series, we're going to change all of this a lot, but this integer is going to be the only thing that is going to stay the same. Okay, so we're only dealing with integer literals today. Okay, so this extends exp. We can duplicate this. Okay, so this one is going to be negation. So we'll be able to take any expression, not an integer, any expression, right? So that we have like a recursive tree, okay? And we will be able to negate them, right? So if we get like 2, we will be able to say -2. And if we get like 2 plus 3, we'll be able to take this whole thing and negate it. All right, and the last one is going to be addition. Add and we're going to be able to add two expressions. The first expression, and the second expression, like this. All right, so now that we have this language, even though we don't know how we can interpret it into our host language, right, the denotational semantics, we can already write programs in it, classic dependency inversion. Okay, so we're going to go into, so we're going to skip the interpreters and we're going to go to programs. Okay, source main, remove the keep. All right, let's create a new file, and it's going to be under Scala, dev inside you, expression, problem, initial, exp. No, we already have the exp, so this one is going to be program.scala. All right, let me go to exp, copy the packages, put it over here. All right, so we're going to have an object program, okay, like this. Cool. So originally what I wanted to do is I wanted to show you these layers, right? So I wanted to have like expression over here, and then I wanted to use, like this visual code feature where I can have, the expression at the top and then the program at the bottom. And in fact, we're going to start doing this, but I'm pretty sure that we're going to start running out of space very, very soon. And so when this happens, I'm going to flatten everything out again. So for now, let's have these expressions over here. Now we're at the level below. As you can see, there's 0, 1 here, there's 0, 2 over here. We're going to have our programs over here. Okay, so we're going to import exp so that we don't have to say exp dot, and we're going to construct an expression, right? Somehow. Okay, so this expression is going to evaluate eventually to 13. Okay, so this is going to be 13, and the expression that we want is going to be this. So we're going to take 16 and we're going to add it to a negated expression of 1. Whoops, negated expression of 1 plus 2. Okay, and this whole thing is 13, right? So this is 3, and this is -3. 16 plus -3 is 13. Okay, so we're basically just going to use this language to construct this expression. Okay, so first we're going to add stuff. Okay, so the first thing that we're going to add is the literal of 16, and we're going to add it to a negation of addition. Okay, and the addition is going to be of the literal 1 and literal 2, like this. Okay, so as you can see already, we're running out of space. This is the entire expression, right? So we have 16 plus the negated version of 1 plus 2. Just as a reminder, in the To-Do app, this is going to be the controller, right? So the web controller, or the the terminal application, the GUI, right? Basically, which will decide what stuff to call on the main language, on the main application. And also one layer below, it's going to be the application, which will decide which methods to call on the data layer. Cool. So now as programmers, the first thing that we want to see is probably this expression being evaluated. However, let's pause for a second and understand how much power we have at our hands. We're seeing the AST, the abstract syntax tree, or the guts of the language. So we can do way more things with it. We can optimize it, we can debug it, we can pre-print it, we can do all of the things, and of course we can just evaluate the expression. In fact, the first interpreter that we're going to write is going to be not the one that is going to evaluate these expressions. All right, by the way, this whole thing is red, not because it doesn't compile, it's because I deleted the .keep file. Okay, so let's go over here, let's do the same thing. As you can see, as soon as I'm going to delete it, it's going to be red, and the whole thing is tracked on Git, right? And I'm going to commit it by the end. All right. So over here, we're going to have new file, same as before, Scala, dev inside you, expression, problem, initial, and this is going to be the first interpreter, and this one is going to be the pretty printing one. Okay, so we will be able to view the expressions. So it's going to be called view.scala. Okay, and it's at the same level as the programs, so we can do something like this. All right, as you can see, we're running out of space. All right, let me do this. All right, cool. So we're going to have object view, and we're going to have a def apply, and it's going to take an expression, right? Any expression. Let me have a bit more space like this so that we can kind of see the whole expression. Okay, we don't need the terminal right now. Okay, so it will take an expression, exp, okay, and it will produce a string. Okay, so how is it going to do this? Well, it's just going to be to pattern match on the thing. Okay, pattern match, and in fact, I believe Matthias should be able to help me over here. Yes, so let's do literals, and let's do, okay, come on, don't give up, don't give up. Literals, negation, and come on, case, and addition. Yay! All right, whoops, All right. Okay. So actually, I don't want to have these imports. So let's go over here and do exp dot. Okay, like this. Let's remove these guys. All right. So what are we going to do? So if this is a literal, then, well, we just need to do n.toString. Now, both of these two cases are going to use string interpolation, so I'm going to use string interpolation over here as well. So I'm going to do it like this. Okay, $n. Basically, convert it into a string. If this is a negation, and then it's going to be an expression, right, which is these parentheses. Then it's going to be negated dollar and whatever this expression already is, but we need to not forget to actually evaluate this expression. Okay, so this is applied. Basically, so not evaluate, but like view this expression. Okay. And the last one is also going to be an expression. Whoops, I wanted to do this. It's an expression. Okay, like this. And we're going to say dollar, and we're going to apply the first one. Okay, and then we're going to have plus, and we're going to apply the second one. Apply E2, the second one. All right, so now everything is fine, everything compiles. Cool, now we can go and see this in action. So we're going to open the main, and as you can see, like I'm already running out of space. Okay, so I'm going to, let me flatten the whole thing. Okay, so we have expressions, and then we have, so we have written the programs first, and then we have the interpreters. Okay, so we have expressions, programs, interpreters. Right now we have only this one, and we have our main method. I can bring up the terminal. All right, so as of right now, it just prints out hello world. So what we can do now is we can just do something like print line initial dot view of initial dot program dot exp, like this. And as you can see, this is exactly the expression that we have. Cool. Just for the giggles, let's also have another way to view these expressions. We're going to just copy paste these guys, put it over here, and we're going to call it prefix. Okay, and over here, let's not forget to call prefix as well. Prefix, like this. All right, so we're going to make it look a little bit Lisp-like. So we're going to have a space over here, and we're going to have this plus over here, and we're going to have a space over here, and just a space over here. All right, and now we can go back to main, duplicate this line, and instead of calling view.apply, we're going to call view.prefix. All right, and as you can see, now our expression looks Lisp-like. Looks like, I believe they're called S expressions. All right, let's finally add the interpreter that evaluates these expressions. Okay, so we have the view over here. So let me actually create a bit more space. All right, so we're just going to create a new file. In fact, I can say new Scala file, and this is going to be an object. Okay, it's going to be an object which is going to be called eval. All right, cool. So I prefer to have packages like this. All right, object eval, same thing. It's going to have apply. Okay, it's going to have an expression. In fact, maybe for now at least I can do this. Come on, like this. All right, so that we can kind of see the similarity to this one. Okay, so it's going to take an expression, but this time it's not going to produce integer. It's going to produce it's not going to produce a string. It's going to produce an integer. Okay, but the pattern is exactly the same. In fact, let me copy paste this. Let me copy this. Okay, let me mark these guys and remove everything to the end of the line. Okay, like this. All right, cool. So enough of the similarities. Let me flatten everything again. So we have view and we have eval. Okay, let me fix the formatting. All right, so if it's an integer, if it's a literal, well, then it's already evaluated. Okay, we don't need to do anything. Okay, if it's some expression, then we first need to evaluate the expression, and then we need to negate it, like this. Okay, and if it's two expressions, then we need to evaluate both of them. Apply 1, apply 2, whoops, E2, and when the values come back, we just need to add them together. Okay, super simple stuff. All right, let's go back to main. Let's add this guy. So this is going to be eval, and this is going to be, yeah, like this. Okay, so now we have our 13. We can see the expression, and we can also see the expression with the with the Lisp syntax. Cool. So now, as already mentioned in the previous video, we're not going to constantly jump between the initial embedding and the final tagless embedding, or the tagless final embedding. I'm going to switch them all the time. All right. So the entire series is going to be focused only on the tagless final embedding, and therefore we can pretty much abandon the initial embedding. We're going to see the similarities just a little bit in the beginning, but we can pretty much ignore it. If you're curious about how to do everything with the initial embedding, then I recommend that you go through the paper at your own pace. All right, so let's discuss the final embedding. So I'm going to go to expression. I'm going to go over here, and I'm going to create a file over here, and I'm going to call it final, and it's going to be as well exp.scala. All right, so let me copy the packages, but in this case it's going to be final, and final is a keyword in Scala, so we need to do this. All right, so over here we're going to have an object exp. Maybe I should show you the other one as well, so that you kind of see the similarities. All right, so this was the initial one, and over here we're just going to have methods. Okay, we're going to have methods, and in fact, you know what, let me do this. I'm going to copy these guys, I'm going to put them over here, and final case class, it's going to be turned into a def, and these guys are going to be lowercase because they're methods. Okay, and over here so extends xp is going to go away. Okay, so these are methods, and now we're going to return an integer over here, and this one is going to be n, this one is going to be negative e, and this one is going to be e1 plus e2. Notice that we don't have expressions, like expression is an object, so we're going to have integers over here. All right, now I know that I just typed it out very fastly without explaining much, but let's start looking at it. Now the first thing that we're going to notice is that there's something weird going on. Everything seems to be intertwined. So over here there was a clean DSL, and over here there was a clean interpretation. Okay, but over here it seems like it's mixed together. Okay, where it seems like we're already interpreting into an integer. For example, how would we do this if we wanted to do it with the strings, right? So for now, let's just hack a little bit. So I'm going to do this. Okay, I'm just going to copy them. Okay, so we're going to do 2 over here, 2 over here, 2 over here. Okay, so I guess this is going to be a string, and this is going to be a string as well, and this is going to be a string as well, and the implementations are going to be so if I'm going to start copy pasting, okay, so this is going to be this. If I'm going to start copy pasting this one, it's going to be weird because it's going to call apply, right? Because everything was here in one method, and was basically recursively traversing this tree. This is also called folding over a tree, but over here we don't have this tree. Okay, so what are we going to have here? And this is where we realize that not all integers are created equal. So we see integers over here everywhere, but if we compare this with the original program, then the original DSL, I mean, then only in the literal we had the integer. All of these others, they were something else. So over here it's supposed to be something like expression, but we don't have expressions over here. So because this thing somehow seems to be intertwined with the interpreters, we should probably use integers over here, and for this guy these probably should already be strings. Okay, so this one and this one, they should already be strings, and therefore over here we should be able to just say e, right? Because it's already already an expression, right? It's already a string. Okay, so therefore over here, if I go into view and I copy this one, paste it over here, let me create a little bit more space. Okay, then again, this one is already going to be the interpreted representation, and over here as well. And now this is how it will compile. So it seems like what we need to do is we need to somehow abstract over this type. And in the paper, what they do is they hard code this type first. They say this is going to be the representation, and it's going to be an integer. And this way we can distinguish between these guys. Okay, so this one is an integer, this one is the representation. And we're going to have a second version of it, which is going to be over here, right? That's going to be repr2, okay, and it's going to be a string. Okay, so we're going to have repr2 like this over here. Okay, and now it's gonna make a little bit more sense. Okay, but so essentially in this encoding right now, at least right now, the DSL is mixed with the interpretation. But we can easily, fix this, right? So notice that in the initial embedding, I just wrote the DSL and then we went ahead and started implementing the program. Over here, we're gonna prettify it a little bit first, okay? So the next thing that we're gonna do is we're basically going to realize that, as you already should know from the previous video, in the tagless final encoding, the DSLs are traits. So basically, we just need to put like all of this information into a trait. Okay, so we're going to create, trait exp, okay, and we're going to put these things inside, and this representation is just going to be the parameter, okay, like this representation. But now that it's not an integer, now that it can vary, we have no idea how to actually implement this. So what we're going to do is we're going to have an object below. It's going to be an object, and this one is going to be val. This one is going to extend the expression, and this one is going to specify that it's going to be the integers, okay? And therefore, now that we know that it's integers, we can actually do this, okay? So we can actually do this. Wrapper is going to turn into an integer. We can make all of these guys abstract. This is abstract. This is abstract. And this is abstract. We don't need this one anymore, okay? And now let's do the same trick for the second one. So we're just going to say that this is going to be an object view, extends expression of strings. Therefore, we can throw this guy out. Let's have a brace over here. Let's have a brace over here. Let's have, by the way, let's add overrides. Override over here. And we're going to have wrapper2 over here is going to be strings. Okay, so now we have our DSL, and we have two interpretations, right? We have two interpreters, one over here and one over here. This one doesn't compile. Why don't you compile? Stop implementations follow, missing implementation for 3 members. All right, hold on, I did something wrong. Wrapper. It's all fine. It's all fine. Oh yeah, they're called 2. Like this. All right. There we go. So we have the DSL and we have the interpreters. And by the way, Metals has this thing. I'm going to disable it because so we can like jump to the parent. Okay. I'm going to disable this real quick. So we're going to go to Metals and we're going to click over here. We're going to go into the extension settings and we're going to go to the bottom and we're going to disable this, at least for now. Okay. Cool. So now all we need to do is we need to put them into their appropriate places. This trait is already in the appropriate place. We just need to remove the object around it. Like this, and let Scala FMT do its own thing. Okay, so okay, we have the interpreters over here, and we're gonna go and we do new file, final slash eval dot Scala like this, and we can pretty much copy this guy, put him over here. We can cut out eval, put eval over here. All right, let's create a new file over here, call it view. Right, so if I'm creating it from the same destination, it's gonna create over here. So let's do that, and cut it out, and put it over there. All right, cool. Okay, so let me start closing things. So I'm just going to close the others. So we have the expression, and this is the final expression. Okay, like this. We're going to have the view, which is going to be the final one, like this. Let's also open the eval, which is in the final one, which is this one. All right, cool. So we have our DSL, which is just a trait, was a parameter. We have the view, and we have the eval, right? Both of the interpreters, they look very, very similar. All right, now at this point, it starts to look very, very object-oriented, right? A simple trait and a simple implementation. However, there is one interesting detail, and it is this parameter. Not only that, but all the return types, right? Every method has to return this parameter. You know, some methods even take this parameter as arguments, but the point is that all of them return this as a result. So if we were to go down to the to-do app and compare it, for example, to, let's take the boundary. Okay, so first of all, this trait does not have a parameter yet because it's not in the tagless final style yet. But if you look at the methods, they obviously return different things. This one returns an existing to-do. This one returns a bunch of to-dos. You know, the one that deletes or, deletes one or deletes many, they all return units. How are we going to make sure that they have exactly the same return type, similar to this guy? And, we're going to see, we're going to have the answer to this in the upcoming videos. But essentially, the answer is going to be high kind of types, right? So it doesn't need to be exactly the same type. It needs to be a type that has exactly the same structure. Cool. So now let's go and see these programs in action. So we have our main over here, and we're probably gonna duplicate this guy like this, and we're gonna do a print line. I'm gonna say new final. Oh, we forgot actually to write the program. Hold up. Let's actually go and write the program. We don't have a program. All right, so we're going to go over here. We're going to say new file, and it's going to be final program dot Scala like this. All right, let me go and do this, and we're going to do that. All right, let's actually open the other program so that we have something to compare against. Let's put it on the left like this, and on the right we're going to have this program. Okay, so over here the program is going to be a simple class program, and it is going to get the expression as the parameter. Okay, so it's going to do exp. Okay, so it's basically the language over here. Okay, and it needs to be parameterized with something, so we're going to have a parameter over here, so it's going to be a wrapper, and we're going to have a wrapper over here. Okay, so it's going to have only one value, which is going to be the representation. Okay, so and the representation is basically going to look exactly like this. Okay, like that. So we're just going to copy this, and we're going to paste it over here, and we're going to mark everything. Just going to make everything lowercase. Okay, and in order for that to work, we need to import exp. Okay, because it's inside of this trait, inside of the exp trait, we have like all of these methods. They all return representations, and we're pretty much done. Okay, so this is going to be our program. All right, let me flatten everything again, and let's go to main. Okay, and let's do what I wanted to do a couple of seconds ago. Okay, so we're gonna have this, and we're gonna have print line new, and we need to instantiate this class. So this is a final dot program. Okay, I'm gonna do final dot eval, and it's going to have the dot representation over here. Okay, let's do the same thing for view. All right, so basically, as you can see, it's kind of sort of like reversed over here. Okay, so over here we were having an interpreter, and it was getting the program as its parameter. Over here it's the other way around. We have a program, and it wants an interpreter. Okay, and now that it has the interpreter, we can see the representation, which is this. We actually also forgot to add the prefix one. Okay, so it's going to be view dot prefix. Let's go. In fact, let's not waste any more time on the prefix. Let's not have it. Okay, let's just throw this guy out. We don't care about the prefix anymore. Okay, in fact, let's throw out the initial encoding. We actually don't care about the initial encoding. So let's throw these guys out, and let's also import final like this, so that we don't have to do this. All right, I forgot to remove the dots. It's too much dots that I'm removing now, here and here. Now we're pretty much done for today. This video is already getting kind of long. For the rest of the video, I'm just going to show you like the typical things how Tagless final would look like in a real application. Specifically, usually you don't see many classes, and you don't see much parameterization at the top level. Okay, so hold on, let me close this one. So we have the expression, we have the view over here. Okay, so for example, this view, it usually would not look like this. It would look like this. It's going to look like this. Val DSL. And this one returns a view of string, okay? And I'm sorry, not the view of string, the expression of string. And therefore, we're going to have over here, we're going to have, say, new expression of string, right? So basically anonymous classes, okay? Like this, and therefore, we don't need to do that, okay? So, no equal sign like this, okay? And therefore, in the main, we're going to see over here, we're going to say view.dsl. Okay, the same thing for eval over here. We're just gonna cut this out, remove that. Okay, and it's gonna say, come on, I wanted to remove that. I'm gonna go over here. We're gonna say eval DSL. It's gonna be this, new this, like this. It's just a thing that people usually do, because like we will see in just a couple of seconds. For the programmer, this is going to be a DAF, because it's going to be parameterized with stuff. Okay, let's go here, eval.dsl. Oops, not comma dsl.dsl. All right, so we're going to do the same thing with the program. Okay, so notice that in the main we need to access the wrapper. So the representation .repr, and so if you wanted to do the same thing over here, we would also need to have a trait over here, right? So it's going to be a program of representation, and it's going to have a def representation. Always have defs in your traits, okay? And therefore, we're going to have like an object over here, which is going to surround the whole thing. Okay, this object is going to be called program. Okay, and now over here, instead of this guy, we're just going to have a def DSL, right? So this time it's going to be a def DSL because it needs to be parameterized with the representation. It's going to take the expression, same as above, okay, and it will return a program of this representation. And how is it going to do this? It's going to say new program of this representation, open the brace, remove this parameter, and let Scala FMT do its job. And therefore, in main, we can go, instead of saying new program, we can just remove the new and say .dsl over here. Right, so it's just kind of like a like a pattern, like a style that usually people do. So everything is essentially a DSL. Now, oftentimes these DSLs are also passed around implicitly, which I don't really recommend. So this is a tutorial, so in this entire series, I'm going to try not to use them implicitly, and not to pass them around implicitly. However, I'm going to show you how to do this. Okay, so if we go to our program and we just make this parameter implicit. Okay, and now we go and make, for example, this eval implicit. Okay, like implicit val DSL over here. Okay, then if we were to go to main, if we had this guy in scope, right? So if we had eval in scope, okay, then instead of passing eval DSL over here, it would be enough. Let me actually do this. It would be enough to just annotate the type. Right, so basically give me the DSL for integers, and it's going to be this one. However, I really don't recommend you to do this. For example, if you bring in the view, it actually might not work. So if I go to view, it actually already doesn't work. See, over here, it already doesn't work. Could not find implicit value of parameter, right? So just because I have this import, weirdly enough, if you go to view, it's not even implicit, right? For some reason, like this already doesn't work, which is super weird, actually. Yeah, so basically don't do this. If you were to do this, and in fact we will end up doing this with the DSLs that are not ours, but with the DSLs that are coming from a library like cats, because they're very mechanical, and they come with a, no pun intended, another DSL, right? So you can import like cats implicits, and then the way you use them, you don't even see the names of them are being used. So for example, over here, if you go into the program, we're actually using this exp, this name. However, like with all of this other stuff that we're gonna talk about, you're not even gonna use the name. And so what people do most of the times is they use the so-called context bound notation that we talked about in the video about implicits and in the video about type classes. Basically, you can go over here and say that this representation needs to have an instance of exp, right? So it's syntactic sugar for this guy, all right? So we can remove this one, okay? But now in this case, we actually need this name, and this name is not there anymore. So we need to retrieve it, right? So we need to do something like val exp equals, and now we need to get it out of the implicit scope like this. Okay, so this is just, again, like this is just a pattern. Okay, let me actually revert all of this. I'm going to leave this implicit over here, even though we're not gonna pass things around implicitly. I'm still gonna leave it over here because most of the DSLs, like if you're looking at a code base with tagless final, you're gonna see something like this, right? Monad, and then like monad error, and then like all of that stuff. I'm sorry, it's not a comma. Right, so it's just going to be like a couple, a bunch of all of these context bounds. Okay, so I just wanted to show this to you as well. But for now, we're going to leave it like this. One tiny thing, you might be tempted to call this method apply, and therefore in the main, you could just basically say something like this. Just oh come on, let's do that. Right. So you basically say, let's make a program with this interpreter. Let's actually remove this one. I don't recommend you doing this. And the reason why is that if we go back to the context bounds, so over here, right? So before I showed you how to like retrieve this thing from the implicit scope, right? And we did something like val exp wrapper, okay? And we did just we just implicitly exp wrapper like this. Okay, so this is what we did before. And by the way, like in I believe that it does that because of the Scala's limitations. Let's do this one. Okay, so in Scala 3, this method is renamed to summon, and it used to be called the, but they're changing it all the time. And also you can define your own if you want. However, in libraries like cats, you usually have a thing called a summoner, which means in the companion object for exp, you would have a method called apply. In fact, let's actually do this real quick. So we would have object exp over here, and over here we're going to have apply, which takes a representation, and we're going to use a context bound again. We're going to say this one needs an expression. Okay, so it's going to return you this repression. So all it's going to do is basically it's going to summon it from the implicit scope, right? So it's basically going to call implicitly for you. Okay, so now that we have this thing, if we go back to our program, we can basically just remove this. Okay, right? Because this works now. Because it's basically calling apply like this. I'm not sure what's wrong with it. Okay, now it's happy. So I guess it was just SPT incremental compilation. Okay, so basically this is how you would get instances out in libraries like cats and whatnot. And therefore, if you call like these guys apply, then you wouldn't be able to distinguish, and oftentimes the compiler wouldn't be able to distinguish the call to the summoner or the call to the creation of the new object. Okay, so in such a small example like this, we're probably not going to run into issues with this, but in the upcoming videos, for sure, we're going to run into issues with this. So therefore, we're not going to call these guys apply. We're going to call it DSL. Okay, let's revert this, and let's also throw out the summoner. We don't need him over here. All right. What does it want? What? Unspecified value parameter exp. What? It's right there. Program Scala SPT. What are you doing to me today? Oh yeah, we forgot to remove the context bound. So you can't have like both the context bound and the implicit parameter like this. All right. Cool. So this is pretty much all I wanted to show you today. Originally, I planned to go like all the way to the higher kinds, but I think we're running out of time, and we're going to do this next time. Let me double check real quick if everything looks clean, and then we're going to commit this. Cool. So I cleaned everything up. I also brought in, at least in the main, the initial encoding. We're going to throw it out in the next video. Also, I renamed the apply to interpret so that it kind of looks better. So we have the eval interpreter, and it can interpret programs. Okay. If we go in there, it used to be called apply over here, so I just renamed it. Okay, I also threw out the the prefix interpreter for the initial view. I just threw it out. Okay, so yeah, so everything else looks clean. Yeah, so let's go and commit it. So I'm gonna go over here, which shows me that I have a bunch of changes. I'm using ZSH, so I have a bunch of aliases. Like for example, this is git add, and gcam is I actually overrode it, so it's add everything and commit everything. So I'm actually going to do gcam. I'm just going to say video 2. Okay, just like that. Okay, there's also alias gp, which is git push. So I'm going to push it. There we go. Come on, let's go and check it, which is over here. So you should be able to click on, let's remove this thing, to click on commits and see the video 2, and you should be able to see everything that we did today. Okay, so we have the final expression, we have the initial expression, we have the eval and view in the final version, we have the eval and view in the initial version, we have the program in the final version, we have the program in the initial version, and we have the main that showcases both of them. And this is pretty much all that we did today. And I don't want to waste any more of your time. As always, it's been Vlad, devinsideyou.com. Don't forget to like this video if you did, subscribe if you want to improve the developer inside you. And if you learned something today, consider supporting me on Patreon, and thus watch my videos weeks or sometimes even months before everyone else. And most importantly, take care.